Hello everybody, this is our study video for Appendix A. What I've done is I've gone back and looked at your old Appendix A test and I pulled out some questions that I thought were really good for practice, and I wanted to go over some of the answers for. Again, the best way to study for this exam is to go over old quizzes and tests. So that's what we're going to do in this video. I pulled out problems that are very specific to Appendix A, but you may find that there'll be some ones that show up that are old from your Chapter 1. So you might want to go back and look at that Chapter 1 video as well to get a full study, get your studying in for Appendix A. So here they ask us to write both a recursive and an explicit equation for the sequence. They don't tell us what kind of sequence it is. We don't know if it's geometric, and we don't know if it's arithmetic just yet. But we can kind of investigate and see what's going on. And again, we're going to want both a explicit and a recursive. And my pen is a little bit slow. I apologize. So we're looking again for an explicit and a recursive. All right. So with this sequence, we're kind of looking for that change. So let's look at how it's changing. You can kind of see that we're increasing by a positive 3 each time. We know that to get to that next term, we're going to be adding 3. And so repeated addition means we have an arithmetic sequence. So when we read our recursive, we know that there's 2 parts to our recursive. We're interested in our 0 term, and then something that's going to generate our next one, so n plus 1. So for our 0 term, we look up here, and it actually starts with our first term. So if we're interested in finding the 0 term, we're just going to go back once by subtracting 3. So we know that our starting term is going to be 4. And then for our recursive, it's going to tell us a rule. We're going to have our starting value and then how to generate it. So what that means is, take the one I'm currently on, how do I get to the next one? So I'll have the one I'm currently on, t of n, and what do I have to do? Well, I have to add 3. And so what we're going to do, is I've shown you the geometric, and we're looking for our arithmetic. So we need to take it and add 3. So really a recursive just gives us our rule. It gives us what we would have to start with and then what we have to do each time. When we get to an explicit's really helpful because maybe we're not so much as interested in the what's going to happen next as what's going to happen a long ways down the line. So for this one, we're looking at a function. T of n is going to be equal to, and so we take that repeated addition. What is repeated addition? Well, it's just multiplication. So 3 times whatever term we're currently on, and then that starting value. What did we have to start with? And in this case, it was a positive 4. So our explicit is going to look like a function, and then our recursive will be some type of rule on how we can generate that function. You will need to know how to find both recursive and explicit, so make sure that you can do both. Moving on. Slowly but surely. If f of x is equal to negative 2x squared plus 9x plus 5, this is to calculate the following. Find x if f of x equals 0. So we can think of our f of x as being like a y. So really y is equal to 0, which means in this case our whole equation is going to be 0 is equal to negative 2x squared plus 9x plus 5. So what we're interested in doing here is factoring. Yay, factoring. So we go to our Xbox method. We'll have our x. What we're going to do is we're going to take whatever our first term and our last term, and we're going to multiply these guys to put it in the top. And so when I multiply this, I'll get a negative 10x squared. Careful of that negative. Common mistake, I think, will be when people forget that there's that negative up front, and then that positive 9x comes down below. So we're interested in what, when multiplied together, is going to give me a negative 10x squared, and when added together gives me a positive 9. So we know that when we're multiplying to we want to get a negative. So in order to multiply to a negative, we're going to need one positive number and one negative number. So we're looking for the negative to outweigh the positive to outweigh the negative. So we're looking at 10x and negative 1x. So we can take and we can plug that back into our box. We're going to be interested in putting our negative 2x squared, our positive 5, and then what we found in the blue with what was missing. We had a positive 10x and a negative 1x. Out to the sides, we have to think about, well, what do 10x and 5 share in common? That's going to be a positive 5. Down below, what does negative 2x squared and negative x have in common? That's going to be a negative x. Careful, that'll be one that'll throw people. And then down below, we're looking at a 2x and a 1. Both of those are prime numbers, our negative 1 and our 5. There's nothing they have in common, but we can still pull out a 1 when that happens. So we have negative x plus 5 times the quantity 2x plus 1, all equal to 0. So really you just take and set those two values equal to 0. And when we solve, we're going to find out, subtract 5 from both sides, you have a negative x is equal to negative 5. Careful, we just want when it's x, so we're going to divide both by negative 1. So x is going to be equal to positive 5, and then we can see that we will end up with a negative 1/2. So let me divide both sides by 2, negative 1/2. Are the two values that will make f of x equal to 0, or our function equal to 0. So a lot of factoring. Factoring is going to start to come up in Appendix A. Then it says that a marketing research team for ACME Home Supplies discovered that for every 250 ads sent out, 18 sales were made. So if Acme ordered 1,800 ads, how many sales should they anticipate? We're looking at something that's set up as a proportion. So we're going to use our proportional thinking. We're going to take what's our known information. So we know that for every 250 ads, we are going to see 18 sales. And so I'm going to think about setting this up as a proportion. So we know if we're thinking proportionally, if we can sell 250 ads, what happens if we have 1,800 ads? I've got ads on top, which means I'll have to have sales down below. And we're trying to figure out how many sales could we get. So let's represent with the variable s. How many possible sales are there? To do that, we can use our cross multiplication method. So we'll cross multiply and have 250 times s is equal to 18 times 1,800, which is going to give me 32,400, and we'll take and divide that by 250, and we find out that we are going to have approximately 130 sales. I rounded that up because my calculator told me that s was equal to 129.6, and because this is a real world problem, we can't have 0.6 of a sale, so we're going to take and round it up. Moving on, so it asks us to create a table and a graph for the sequence. Alright, so let's do that. We've got a table with our x and our y. So we can start as low as 0 and build up. We know that our first term is going to be a 3, our next term is a 6, and then for this one, let's pretend that it's an arithmetic sequence. So we know that we're increasing by 3 every time. So when we plot these on a point, remember, we can't have any negatives, so we're just looking at plotting each individual one. We also can't have half or any negative numbers. So we're going to want to plot these as points and not a continuous line. So we've got 0, 0, 1, 3, 2, 6, 3, 9, and if I continued the pattern, we would just have those points plotting. Again, we're just looking at plotting the dots because it's not continuous. We can't have half, a third, any fractions, or any negative numbers. All right, and you should be able to do that for both the geometric and arithmetic sequences. Create a table based on a sequence and then graph your table. I believe this is our last one for Appendix A, and in this one we're interested in the details. So first what we're going to do is when we investigate it, we're going to want to graph it. So not part of my details, but some information that'll make it easier to solve would be if I were to create a table. If I plug in 0 for x, I'm going to have 3. If I plug in a 1, I'm going to have 6. If I plug in a 2, 2 squared is 4, 4 times 3 is 12. And so we can see how it's jumping pretty rapidly after that. So on this graph that they provided with me, I'm looking at 0, 3, 1, 6, and then 2, 12, which is going to go all the way off the page. And we know that this will be connected. All right, so let's think. Can we have negatives? Could we have had negative values? We know that we can raise negative exponents, and so this is going to look a little bit differently. I haven't included all of them. Let's go to the calculator and see what it's going to show me. So I'm going to my y equals screen, clear out what's up there. And we are looking at the function 3. Oh, sorry, it's freezing a little bit on me. 3, and then what we're doing is we're taking and we are raising 2 to its power. All right. Well, let's make sure I only have 1x. Beautiful. So I can take this to a table, and we can verify some of those values that we looked at earlier. That's 0, 3, 1, 6, 2, 12. If I look, I can have a negative. It's to the negative first power. We're looking at 1.5. Negative 2 is 0.75. And as we keep going, we can kind of see that it's going to get smaller and smaller and smaller. And it looks like it's not quite going to ever reach 0. So when I take that and look at that on a graph, whoops, sorry, they're running a little bit slower. We can kind of see what's going on. We've got that behavior where it looks like it's reaching an asymptote at y is equal to 0. And then continuing on. So if I go back to what I had graphed, we can kind of remember how that was going to keep getting smaller, but never really approach 0. So when we talk about our domain, we were able to plug in any number. We could have fractions, we could have negatives, we could have whole numbers, and so our domain is that x is going to be sandwiched in between negative infinity and infinity. Our range, we talked about how we had that asymptote at y is equal to 0, so y can be any value that's greater than but never equal to 0. We have that asymptote, so let's write that one down. At y is equal to 0. We don't have any lines of symmetry. We don't see any symmetry there, so there's no symmetry. We can kind of see we had that y-intercept. So we had a y-intercept of 0, 3, but we had no x-intercepts because we know that x can never, or sorry, that our y can never be 0. And here we've got tons of details, lots of things we're talking about the symmetry, the asymptotes, domain and range, our intercepts. All those things are great details that you can use. Please use your graphing calculator. It's a great tool that kind of allows you to check your work, see what's going on, and then be able to explain what's going on. So please graph it and give me some details about what you see, what the graph is telling you. That's going to conclude our video for Appendix A. I hope you found it helpful. Please go back and look at your old test. All right. We will see you. Have a great weekend. We'll see you on Tuesday for the for the Appendix A portion. Have a nice weekend, everybody.